Okay, thank you for the invitation to participate in this session, and congratulations, Bala. Okay, so this talk is going to be the least likely to be useful talk in this session. The talk is based on work done by Emparan, Suzuki, Tanabe, and collaborators in these papers, and by myself, my colleagues, my students, my postdocs, by the Indian group in these papers. Okay, so let's go. As everyone in this room knows, something that's totally remarkable about black holes as opposed to, for instance, supernovas, is that though they undergo very complicated dynamics, the dynamics is governed by very simple and very beautiful equations we can write down on a t-shirt. These are the equations. It's Rmn equal to 0. The difficulty with the statement, of course, is that while these equations are easy to write down, they're difficult to solve, at least analytically. And one strategy for progress in such a situation is to try to enlarge the problem by including a natural parameter into it, and then try to solve the problem at different value of the parameter. Hopefully that will teach you something about the problem at the value of the parameter in which you're really interested. In this talk, I'm going to adopt the strategy. In the main talk of this talk, in this talk, my parameter will be 1 by d, where d is the number of space-time dimensions. Okay? Fine. So let me explain how I'm going to work. Consider a d-dimensional Schwarzschild black hole boosted to velocity um in coordinates that are probably that may be unfamiliar to you. These are called Kerr-Shield coordinates. So these coordinates here are just sort of a perverse way of writing the familiar Schwarzschild black hole in a frame in which the Schwarzschild black hole is moving. Okay, the speed of the center of mass motion of the black hole is um. Is a constant velocity vector that squares to -1. Okay, so that's what I've written here. And this function r is defined in some complicated way. If was just rest, r would be the spatial radial coordinate to the position that we're talking about. Something that you notice here, by the way, is that you're writing the metric of interest in terms of quantities that are naturally defined in Minkowski space. So you're using quantities in Minkowski space like this coordinate r or this velocity field un to build a metric that's not Minkowski. Okay, now Emparan, Suzuki, and Tanabe in this paper a few years ago made the following simple but key observations. First, they observed that in the limit d goes to infinity, if r by r naught is held fixed to any number greater than 1, and you take d to infinity, then this number goes to 1 over this number goes to 0, and so this metric reduces just to Minkowski space. Okay, so this tells you that if you stay a fixed distance, a fixed ratio of the Schwarzschild radius away from a black hole, and then take d to infinity, you can no longer distinguish the space-time that you're looking at from flat space. This is an obvious statement, but an important one. The second thing they noticed is this. They asked the question, how near do you have to go to the black hole before you start seeing that this is a black hole rather than Minkowski space? In order to answer that question, you do this change of coordinates. Let r equals r naught, the Schwarzschild radius, into 1 plus capital R by d minus 3, and keep capital R fixed while taking d to infinity, instead of keeping r fixed as we did before while taking d to infinity. And when you do that, the metric becomes this guy, Minkowski plus some deviation that is now not 0. It's proportional to e to the power minus r. What this little calculation tells you is that the distance away from the event horizon that you have to go before you start, the distance beyond which you can no longer see that there is a black hole is Schwarzschild radius divided by d. It's d minus 3, but d and d minus 3 are more or less the same when d is large. Okay, so the key point here is that we have a simplification for black holes at large d. And that simplification is that there are two length scales in the problem. The first is the length scale of the Schwarzschild radius. That's r naught. The second is the much smaller radius length scale, which I'm going to call the thickness of the black hole, which is r naught divided by d. Okay? When d is large, the black hole becomes very much like a codimension 1 object. Okay? Because r naught divided by d is almost 0. Now, is this just a cute observation, or is it good for something dynamical? This question was also asked by Emperor Suzuki and Tanabe, and they did the following calculation. They computed the spectrum of quasi-normal modes in the black hole background at large d. And they found something interesting. You see, you have a quasi-normal mode at every value of the angular momentum in the black hole. Okay, you have an infinite number of quasi-normal modes at every value of the angular momentum of the black hole. What Emperor and Suzuki Tanabe found was this, that at every value of the angular momentum, okay, most of the quasi-normal modes have frequencies of order d divided by r naught. So very, very heavy, very, very fast frequencies. However, there were a finite number of modes at every angular momentum that remained light in the limit d going to infinity. Their frequencies continue to be of order r naught, 1 over r naught. Okay? Now, this is an interesting situation to be in, where you take a problem which has an infinite number of very heavy modes and a few light modes. Whenever that happens in theoretical physics, it's usually the case that there is an interesting nonlinear autonomous theory of the light stuff. Is that true in this case? Can we find that theory? The answer is a yes, and I'm going to tell you about it. Like Ashok, I will not give any derivations, I'll just tell you answers, but I'll tell you enough structure so you can understand what the answer means. Okay, so the way it progresses goes as follows. Consider a metric, which is Minkowski space metric, times this quantity, which is meant to remind you of what you saw with the Schwarzschild black hole. Okay, n here, okay, rho is just any old function in Minkowski space. It's kind of function which becomes less than 1 in a certain region inside a ball and grows larger than 1 outside. N is the normal to rho, it's d rho, del mu of rho, normalized, where the normalization happens in flat space. Okay, and U is any one-form field in flat space. U squared is equal to -1 in flat space. Okay, so once again we're using the strategy of building a metric using quantities that have natural geometrical definition in flat space, in Minkowski space. Now consider this metric. This metric is just a metric, so far it solves no equations, but there are many interesting things about this metric. The first thing that's interesting about this metric is that when rho exceeds 1 by more than 1 by d, this metric reduces to flat space. The argument is the same as the argument we gave at the beginning for Minkowski black hole, for the black holes. Okay, a number larger than 1 to the power infinity is infinity. Okay. Therefore, something interesting is happening. So this metric here describes flat space and then some region where something interesting is happening. Let's call the surface rho equals 1 the membrane, because that's the transition region. Okay? Now, it's an easy calculation to do to check that the norm of the normal vector to rho, the normal one form d rho, when you compute its norm in this metric rather than in flat space, that one form field which was normalized to have metric norm 1 in flat space has norm 1 minus 1 by rho to the power d minus 3 in this metric. And in particular, rho equals 1 becomes a null vector. So rho equals 1 is a null manifold of this metric. That's an exact result. Okay, great. Now, this null manifold actually will turn out to be the event horizons of the black hole solutions we'll construct. Okay. Now, so far, this is just observations. But there's a sort of, to me, interesting result, which I'll tell you about. Suppose I took that starting metric form, this thing here. Remember, it was parametrized by any old function rho in flat space and any old one-form field in flat space. But now I put some conditions on this. I demand that this rho function is not completely arbitrary, but is that 1 over rho to the power d minus 3 is a harmonic function. Suppose I choose that function to have that form. And I also demand certain conditions on this U field, this one-form field. I'll tell you about the conditions in a minute. Then one can show the following. One can show that while this quantity here is, of course, not a solution to Einstein's equations, it can, order by order in a 1 by d expansion, to every order in that expansion, be corrected to a metric that solves Einstein's equations. And when you do this correction order by order, the condition that the U field has to obey gets successively corrected. Now, what is this condition that the U field and actually also this rho field has to obey? Okay, at every order in the 1 by d expansion, the constraint conditions for this thing to work takes the form of a conservation law. Conservation of a local stress tensor. This local stress tensor is the stress tensor of some fictitious object that lives on the surface rho equals 1. That's this delta function here. Okay, this stress tensor has only components normal to this fictitious object. Okay, so you can think of it as a stress tensor of this object. I'm going to call this object the membrane. Okay, and Einstein's equations in an order by order and a 1 by d expansion give you a specific form for the stress tensor. The leading non-trivial order, the stress tensor takes the following form. The stress tensor is the sum of a fluid part plus what we call a total derivative part, a sort of Brown-York type piece. And remember that the equations of motion were conservation of the stress tensor. That's why I've separated this Brown-York piece from the fluid part, because Brown-York stress tensors in flat space on any surface are automatically conserved. The fluid part is the sum of a shear term, so like a viscosity term, and a sort of pressure term. This skated here. So it's a viscosity term and the pressure term. The pressure is a complicated function of the velocities and the extrinsic curvature of the black hole, of the membrane, viewed as a surface in flat space. Okay. Fine. Now, I want to quickly do some counting for you. You see, I don't have the time to go through all of this. You know, there were d stress tensor conservation equations in space-time. One of them turns out to be identically obeyed. I don't want to tell you why. So there are d-1 effective equations. The number of variables in our problem is the shape of this rho equals 1 surface, that's one variable, and a velocity field that lives on this rho equals 1 surface. Now, a vector field living on a codimension 1 surface has d-1 components, but this is a velocity field. It obeys u square equals 1, so it has d-2 independent degrees of freedom. Total number of independent degrees of freedom, d-2 plus 1, which is d-1, equals the number of equations. So we've got a system where the constraints of this 1 by d expansion give you as many equations as variables. This is a good situation because it tells you that the constraint equations plausibly form an initial value problem, okay, for our system. I mean, to the extent that, for instance, relativistic Navier-Stokes equations form an initial value problem for your system. Okay, the equations of motion that you have here are essentially hydrodynamics on a dynamical surface. Hopefully, in an appropriate sense, define a well-posed initial value problem. At least if you linearize around a sphere, for instance, they do form a well-posed initial value problem. More complicated questions of differential equations, God knows. Okay, the membrane in question has many interesting other structures. First, it turns out to host an entropy current, which you can show always has positive divergence. Del dot J is a total, it's a perfect square. And the fact that the thing on the right-hand side here is positive is a reflection of the Hawking area increase theorem. It's a Hawking area increase theorem pulled back to the membrane. Okay, you can ask about radiation. There's something a little puzzling. How can something on a codimension 1 surface obey local equations if it's also radiating? Shouldn't radiation here affect what's going on there? Turns out the way this is consistent is that there is just a simple kinematical fact in large D that certain kind of sources, namely sources that vary on length scale 1, in a large number of dimensions, produce radiation fields that are down by 1 over d to the power d. 1 over d to the power d is non-perturbative in the 1 by d expansion. So radiation in order by order and 1 by d you just don't see. Okay, so this is a situation in which everything's happening locally here, nothing's radiating, it's conservative dynamics, but interesting dynamics. Okay, now, I probably don't have much, how much time? This is like 3 minutes, great. I told you, I want to emphasize that these general equations, these general membrane equations are good for arbitrarily complicated dynamics. Okay, but they're very complicated equations, they're like hydrodynamics, okay, they're nice equations, but you generally can't solve them. However, there's one place where you can make significant progress, where you specialize to stationary solutions. When you specialize to stationary solutions, you can show that the only stationary solutions of these equations are solutions in which u/mu is proportional to Killing vector of the background spacetime. If in the case of Minkowski space, this would be sum of a translation and rotation. Okay. And you can show that once you plug those into our general equations, it amounts to the condition that this quantity k tilde, which I defined somewhere, I define somewhere behind this quantity here, some complicated looking quantity, is almost constant, more precisely, k tilde times the square root of the norm of the killing vector is constant. So this is sort of like a constant extrinsic curvature condition that some of you might be familiar for occurs in soap bubble studies. Okay, now this is a very simple equation and can easily be solved in many situations. Okay, so it's easy to control all stationary solutions of these equations. Now, there are interesting formal properties of these stationary solutions. In particular, these stationary, while all solutions of these membrane equations cannot come out of an action because these equations are dissipative. And dissipative equations don't like actions. Okay? Stationary solutions are not dissipative, so they might like actions. And it works. There's a nice action that generates action for the shape of the membrane that generates these stationary solution equations. The action has interesting thermodynamic significance. The action evaluated on shell is the log of the partition function of the membrane. Captures all the thermodynamical properties of the membrane. There are nice, interesting formal structures of this whole thing. Okay. One or two last things I want to tell you about this is that now, in the case of stationarity, if you take our leading order membrane equations, ones I've presented in these slides, and you compute the simple static solutions of these equations. For instance, I told you about everything in flat space. We can generalize it all to work in ADS space, for instance. So let's do that. You take a little black hole in ADS space, and you compute the thermodynamics of a spherical ball there, and then compare it to what you get out of Einstein's equations. Turns out that the answers that you get out of those membrane equations are exact. Even though they were derived and were guaranteed to be correct at large D, they work actually exactly even at D equals 4, at every value of D. This is only true for simple stationary solutions, simple static solutions. Rotating black holes are more complicated. Of course, they work at large D. Maybe possible to improve these membrane equations so we can get rotating black holes also exact at finite D. That's not been done. Okay, you can linearize about stationary solutions, reproduce quasi-normal mode frequencies, and check that the quasi-normal mode frequencies, reproduce basically fluctuation frequencies for fluctuating modes around this black hole, and check that these quasi-normal mode frequencies agree with the light frequencies of Emperor, Suzuki, and Tanabe, the thing that started off this whole program. So what we're doing here really is computing the nonlinear theory. The membranes are the nonlinear theory of the light modes of Emperor, Suzuki, and Tanabe. Okay, all that I've said here, I believe is correct. What I say here may have no value, but let me say it since, okay, maybe I should just stop. But okay, let me just say it anyway. Okay, what does all of this have to do with astrophysical black holes, which unfortunately live in D equals 4 rather than D equals, I don't know, 80? Okay, what does this have to say about them? Maybe very little, but let me just say a few words. As you all know, black hole collision processes involve 3 stages. There's this in spiral, okay, there's the bang, and then there's the settling down. Settling down can be divided up into a non-linear part and a quasi-normal linear part. The most obvious possible application of these ideas, if there's any possible application of these ideas to astrophysical black holes, is in the non-linear part of the settling down process. To the extent that you can ignore radiation, that's actually, in a way, the main approximation of the large D approach, ignoring radiation, which is exact at large D. At large D, it's not an approximation, but to the extent that it approximates D equals 4 behavior, it's an approximation. To the extent that radiation is not very important, the nonlinear settling down process might conceivably, to a reasonable accuracy, I don't know, just put 25%, 20%, something like that, be captured by our membrane equations. That sounds not even in D equals 4, that doesn't sound totally out of the question to me. Whether that would be useful or not, I don't know. Our membrane equations are complicated nonlinear equations. Solving them is roughly as complicated as solving Navier-Stokes equations. Maybe it's easier to solve Einstein's equations. I don't know if that's progress or not. But anyway, something else that has not been done that I think would be nice to do, and this is my last slide, is this. I've not been able to give you all the caveats of this talk. But one of the caveats is that everything that I've talked about only works when the membranes in question vary on length scales large compared to 1 by D. Okay? Now that presumably works well in an interesting black hole process like a black hole collision, well after the collision. However, the time of the collision and for times of order 1 by d around that collision, these membranes are singular on the scale 1 by d. Okay? So for this collision process has not even accurately been computed in the 1 by d approximation. Our membrane ideas don't go through there. A new approximation scheme would be needed for that. It's conceivable that by working enough, we could accurately understand exactly what happens to a black hole collision at large d. There would be this violent collision process, some approximation where the membrane sort of starts taking over, and then the membrane equations. While no radiation is emitted once the membrane equations take over, radiation is certainly omitted during the collision process. It's possible that an order 1 fraction of the initial energy is radiated away as radiation in the collision process. If so, it suggests that at large d, what happens when two black holes collide is a sharp pulse of radiation over a very short time, and then you see nothing. If that's true, it would be nice to compute exactly what you see. It's also possible that very little is emitted. I don't really know. Okay, thank you.
Maybe take one quick question for Shiraz.
So can you get the black hole scattering matrix in the large d limit, or?
What do you mean black hole scattering? Meaning two black holes?
Yeah.
Yeah, so, okay. I didn't say it well enough, but when two black holes come together, there is a region, namely where, when they come together in large d, each of the initial black holes is a spherical membrane or a rotating ellipsoidal membrane. Those are easy, of course, to compute. Now there is a region of time when they collide in which our membrane equations don't apply. Okay, that region of time presumably persists for a time of order 1 by d, after which this part desingularizes. The membranes connect with each other, after which our membrane approximation takes over. So the motion from here on till the settling down of this into one black hole we could, in principle, capture using our membrane equations. The actual collision process has never yet successfully been computed, even at large d. Though I suspect that if one really wanted to know the answer to that question, one could find the answer. It requires some new creativity.
Maybe we can hold off the questions for later. Thanks, Shiraz.